In this lesson, we're looking at the conversions between vector equations of lines in vector form and in parametric and Cartesian form. So we'll start off in 2D. We know that the vector form of a line is RT is equal to the original position plus displacement vector multiplied by the parameter t. Now in 2D, this A value in storage vector form consists of two components, A1 and A2, and the direction vector consists of two components as well, D1 and D2. So they're the directions in the different components multiplied by the parameter t. So that means we end up with the vector equation of a line looking like A1 plus D1 multiplied by t, and A2 plus D2 multiplied by t. Okay, so this is vector form. If we want to convert into parametric form, then we're looking at x is equal to A1 plus D1t, and y is equal to A2 plus D2t. That's nice and easy there. And then followed by the conversion into Cartesian form, where we can isolate the t value. X subtract A1 is equal to D1t, and therefore t is equal to x take A1 on D1. Now if we do the same for, when we look at the y equation, we can say that y subtract A2 is equal to D2t, and therefore t is equal to y subtract A2 on D2. So because both of these equations are equivalent to t, we can write our Cartesian form of the equation as x take A1 on D1, and that's equal to y subtract A2 on D2. We'll look at how that works functionally now when we go through an example. Okay, so in this example, we're looking to show the vector equation of a line R in parametric and Cartesian form. So if we start by looking at R in vector form and converting into storage vectors, we have 1 and 5 plus t and 2t. And so that means we end up with 1 plus t and 5 plus 2t. So you can see how that relates, particularly if we write that one as t plus 1 and 2t plus 5. So you can see how those values and those coefficients and so on relate to the a and d values. Okay, so that's our vector form. Parametric form, we've got x is equal to t plus 1 and y is equal to 2t plus 5. And then in Cartesian form, we can say that t is equal to x subtract 1 and 2t is equal to y subtract 5, and therefore t is equal to y subtract 5 on 2. And when we equate those two, our y take 5 on 2 is equal to x take 1. We have y take 5 is equal to 2x take 2, and y is equal to 2x plus 3 is our overall equation. So this is our Cartesian form. Essentially the conversions are just that. So we can convert those equations of a line from vector to parametric to Cartesian form in 2 dimensions. In 3 dimensions, our vector equation is going to be RT is equal to, just like in 2D, the initial position plus the direction multiplied by the parameter t, which means we're looking at 3 components now, A1, A2, and A3. So the I, J, and K components, D1, D2, and D3. The I, J, and K components in the direction vector. And that means we end up with A1 plus D1t, A2 plus D2t, and A3 plus D3t. So there's our vector form. To look at parametric form, we will now have an x, a y, and a z equation. So x is going to be a1 plus d1t. Y will be a2 plus d2t. And z is going to be a3 plus d3t. So as this leads into our Cartesian form, the idea is to isolate t for each. When we isolate t for the x equation, we'll have x subtract a1 and divided by d1. When we isolate t for the y equation, we'll have y subtract a2 on d2. And when we isolate z, when we isolate t for the z equation, we end up with z subtract a3 on d3. So 1, 2, and 3. And when we equate them all, we get x take a1 on d1, y take a2 on d2, and z take a3 on d3. So in 3 dimensions, we're not going to do anything more with that. That will be what we use to represent the Cartesian form of the equation. We cannot turn it into an equation that represents those 3 variables. Okay, so as an example, so in this example, we're looking at the 3-dimensional vector line equation, and we want to show it in parametric and Cartesian form. So if we start by looking at it in storage vector form, that's the most efficient way. We have 5, -2, and 4, and we're adding on t multiplied by 2, -1, and 3. So in storage vector form, it is 5 plus 2t, -2 take t, and 4 plus 3t. Okay, so as we convert them into parametric equations, we get x is equal to 5 plus 2t, y is equal to -2 take t, and z is equal to 4 plus 3t. Okay, so then into Cartesian form, isolating t with respect to x, we get t is equal to x subtract 5 on 2. Isolating t with respect to y, we get t is equal to -2 take y. And isolating t with respect to z, we get z subtract 4 on 3. So that means that x take 5 on 2 is equivalent to -2 take y, and that's equivalent to z take 4 on 3. Okay, so there's our solutions as our parametric equations, and here is a Cartesian form. We'll look at a couple of extra examples. Okay, so in this example, we're looking for parallel and perpendicular lines or vector equations that pass through the point 132 to this equation R. All right. In order to do this, obviously, the goal is to write a vector equation. We know that the direction vector is -I take 3j, which will be important. For the first one, for the parallel line, then we should know that A is equal to I plus 3j plus 2k, because that point 132 can be the starting point. And because it's parallel, then D will just be equal to that -I take 3j. So in this case, it's nice and simple. That parallel, parallel is going to be I plus 3j plus 2k, and in the direction -I take 3j multiplied by the parameter t. Perpendicular, A will still be the same. To determine the value of D, we know that the direction vector D, dot product of it, and the current direction vector, which is -1, -3, must be equal to 0 if they're going to be perpendicular. So really what we're looking at is d1, d2 dot -1, -3. That will be equivalent to 0. So we got -d1 minus d2 is equal to 0, and that means we have negative d1 is equal to 3d2. Now, what this means is there's going to be infinite solutions. So if we say if we're looking for one solution, when d2 is equal to 1, so when d2 is 1, then d1 must be equal to negative 3. Then we can use d is equal to I take 3j. And that will be one of the perpendicular solutions, which means our perpendicular line, so we'll say R perpendicular will be I plus 3j plus 2k. And we add on our direction vector, I take 3j multiplied by the parameter t. And there we have it, there's our parallel and our perpendicular vector equations of lines.